And I read about Chris a while ago. It was in the paper, and then I went back to the article, which was originally in the Engineer magazine, which is very good. Get a free subscription to it. So I'm going to read a small quote and then a little description. And I think this was from the magazine, but I think it's quite useful. Engineering design, it's your mind that matters when it's mind over matter. This was Chris's quote, which I thought was very nice. And he described, it says, engineering, according to Wise, is an art, not a science. And the fact that it's considered to be a branch of the sciences by educationists and the government is an important factor in its poor image in society. While many in the engineering establishment bemoan the low numbers of graduates in recent years and wonder where the next generation will come from, Wise argues that the role of engineers has been fundamentally misunderstood, and that we might not need more engineers at all. What we need, he says, is different ones. And I think he makes a distinction between, well, he makes the point that this kind of separation between art and science is really not very useful at all. So, and also, he also does some very interesting projects, which we'll talk about tonight. So thanks very much for coming, Chris.
Thanks. Can everybody hear me? This is the name of our new educational company, so it's free advertising. That's why I changed the title. It's not yet in existence, so don't anybody think about even taking the website, because we've already got it actually. Now, nothing changes very much. This is 30 years ago. In fact, I need my glasses on because I can't see what I'm doing. There's a bloke called Florman, wrote a book about the existential pleasures. It's a bestseller of engineering. And in the preface, he said, "What's it like to be an engineer? At the moment, the profession has achieved unprecedented successes and simultaneously is being accused of having brought our civilization to the brink of ruin," that was 30 odd years ago. People are still saying that. I mean, we're largely blamed for all the technological ills that the world's facing. Also, never praised for things that we've managed to do which have been successful. And in the context of what's happened in the last 30 years or so, there's been a shift in a number of things. I mean, the first one is that we're living longer. You're living longer. Hopefully, I'm going to live much longer. And as time goes by, the proportion of people who are living to 70, 80 goes up. That means, in a funny way, there's less people working to support those who are in retirement, or you're going to have to work longer, which is not necessarily a very nice thought. The most likely thing is we have to work a bit longer because the pension pot's too small. Now, you may say, what's that got to do with all this? If you know anything about technology and technological waves, these are things called Schumpeter's waves, which are technological waves going through the years. And starting with the Iron Age, Steam Age, electricity cars in the 1900s, aviation from the 50s onwards. We're in the digital age now, and we're at the peak of it. People have said to me that the next century or so is the century of biology. And so genetics, robotics, simulation of nature could be very, very important. But if you plot back these waves, you find out they're getting closer, shorter. So the digital age, which really started big time around about 1990. I mean, before that, we didn't have, and I used to work for Arabs. It was only, I think, in 1986 we all got a PC, one PC each. So, in fact, it might even have been 88 or 90, I can't really remember, but it was around about this time. So, although there was fledgling stuff before that, not much. But the waves are getting shorter. Now, if you couple that with getting older, you realize that you're likely to see at least 2 of these waves in your lifetime. Whereas previously, when you died young and the waves were longer, you were in a fairly stable world. So the pace of change that we're all occupying, the world we're occupying, is happening faster, and we're living long enough to see a couple of cycles. So you've got to be very adaptable. And I'm an engineer, as Will said, but engineering is a very difficult thing to work in. I mean, people run away from you when you go to parties and stuff like that. If you can hear this.
Yesterday, I left him alone for a minute, and he disassembled the TV, our clock, and the stereo.
That's perfectly normal. Kids take things apart.
Oh. The part that worries me is he used the components to build a ham radio set.
Oh dear.
Is that bad?
Normally I'd want to run an EEG on it, but the machine isn't working.
What is it?
I'm afraid your son has the knack.
The knack?
The knack. It's a rare condition characterized by an extreme intuition about all things mechanical and electrical and utter social ineptitude.
Can he lead a normal life?
No. He'll be an engineer.
You missed the punchline. No, he'll be an engineer. Can he lead a normal life? No, it's impossible. If you can fix things, you cannot lead a normal life. One of the arts graduates at Imperial, where I used to teach, said this about engineers: somebody who's good with figures doesn't have the personality of an accountant. Can you? Well, just to test that. I mean, can you? Well, I won't ask you if you can name an accountant. Can you name an engineer? Present company accepted. Any offers? I'll ignore that. Brunel, very good. Keep going. Jane Wernick, very good. Newton was a philosopher and a mathematician. Sorry? Physicist. Yeah, keep going. Anybody in amongst apart from the people at the front? Pardon? Sandy Island Perth Traveller, yeah. Any more? Yeah. Yeah. We're getting down to our next door neighbour, shit. Okay. Do you know, if you ask this question of engineering students, who is the person that they come up with? In fact, 95% of all engineering students can't name a single engineer. It shows you how much they know about the world they occupy. 95%.
But they're not taught the history of engineering, are they?
This is when they come in, when they've chosen to do an elective subject, which is torture. I mean, it's 4 years of torture at university, and then you have to go out and practice, and you have to, study really hard to get chartered. These guys can't name one single role model, not one. 95%. I'm not joking. We did this 7 years running at Imperial. The 5% who did name somebody, who was their most popular pick? There was no one that's been mentioned so far. It wasn't Brunel, for example. It wasn't O'Barrett. Nobody knew that he was actually a person. Who else? Who? Give up, guys. Okay. There we are. Norman Foster, that well-known engineer. He is the number one pick of the engineering students. So it shows the sort of their insight. Pardon? I actually think, no, he's nothing like Adolf Hitler. I do think that he's actually a very good engineer, but he's not a professional engineer. He's very, very good at engineering, as it happens. But they can't. Anyway, so these people who work as engineers don't have any idea of the world that they're going to occupy, because they can't project themselves onto a single person who does what they do. Not one. And it's if you look at people, of course you can't tell. I mean, there are 2 engineers in this group, and it's impossible. This one's Norman Foster in drag. No. I mean, it's what is engineering? I mean, these are my kids, and they are doing engineering. They're sort of messing around with the physical world and doing stuff. Every child experiments, makes things, puts things together, plays around. And in fact, we all do bits of engineering. But it's like being a fast bowler. You might be quite a good natural cricketer, but when you go to school, you get exposed to coaches, and they teach you how not to do what you're naturally good at, as a result of which you become average. So it's a very human thing, engineering. As Will said, I personally don't think it's science. And I'm not going to go on about this much, but just to explain the difference. Science is a process of looking at something trying to work out what's going on, and then coming up with some sort of theory which explains it. So it's external to internal. It goes from the physical world, or sometimes the theoretical world, and comes inside your head. Engineering and architecture start here, and then they go outwards, and you're trying to make a physical product. The process is backwards. So you try to put something into the world which comes from your ideas. I mean, to give you an example of the sort of stuff that people do, this is a piece of, an example of a piece of engineering that came from somebody's head. And a little while ago, we did a program with the BBC where we were trying to put this guy's ideas into practice, see whether or not they worked.
If we want to go over there, for example,
well,
a right angle, can we do that?
Steerable in light winds. I think the wind
It's a human-powered airship designed to
the
be
question that needs to be tested is how much speed can you actually get from it?
flown by the French Navy in 1783.
Chris is model building too. He's been working on the propulsion system to see if there are any flaws in Mersnier's design.
So just constructing this magnificent piece of equipment and thinking about it and designing it, that's a piece of engineering. Observing what happens to it, whether it works or not, is science. You might see it like a trivial distinction. It's the difference between research and practice. But they didn't have propellers in 1783.
For now,
so they
the
had to
chain
invent
that will
these
connect
things
the
first.
propeller and hand crank is made out of strain. But does it work as Mersnier planned?
Oops. Which is exactly, we don't want that to happen 1,000 feet up in the air.
No.
No.
Can you lift it up just a little to see if it will float at all?
Hey!
Now this is a piece of science, as a result of which you'll see we did have a piece of engineering.
But not for long. They need to find out why.
This is rubber-coated cotton filled with hydrogen, which is explosive.
Although they've done their best with the rubber coating, the seams aren't gas tight.
We haven't actually tested the seams at all, and we need to concern ourselves with how to actually seal them.
Because they're worried about it catching fire, they want to test what would happen if a spark, say from the propulsion system, got near it.
Wow! That was convincing.
Okay, so that was science. So, I mean, it's fairly obvious.
Ian Ashpole is adamant that they should replace the hydrogen with helium, a safe, inert gas that most modern balloonists use. To float.
Now, this is an example, coming up as an example of the appliance of science. If you do physics at school, you learn about Archimedes' principle, which is about buoyancy. I don't know if you study that sort of stuff. This is a physical demonstration of that. So it's an experiment to see whether or not that works.
The airship, they take out some of the sand that's weighing it down, until it begins to lift off the ground.
So where are we going? Because the training I've done for this.
We're moving a quarter of an inch at a time. Outstanding.
The weight is so finely balanced that pouring out just a few handfuls of sand makes a difference.
Here we go.
To succeed, they still have to turn around and battle back against the wind.
This is good. That's the chains looking good, baby. Here we go, guys. We're turning 10. Okay, let's keep it going. We got it. Okay, right to the wind, straight to the wind.
Will they be powerful enough to combat the wind? It's only blowing at 3 miles an hour, but it could stop them dead.
It's quick. Yeah, we're actually making it upwind. Are we? Yeah, I think we are. We are moving. I think we are moving. We are, yeah. I see a spot on the ground and we are going forward.
Against all the odds, they're doing it. Just as Mersnier intended, they're propelling the airship with human power.
Now, the funny thing about that is, I mean, of course, that is a piece of sort of old-fashioned engineering where you just make stuff and you try it out and you do it. Every time you design a building or a master plan, that's exactly what you're doing. You're coming up with something from scratch. You've got no idea, really, at first, whether it's going to work or not. Not the faintest. And so there are massive, although we've never designed before or since an airship, I mean, the parallels between that and architecture and engineering are very strong. Engineering is the opposite of science, as I've said. I mean, we have this rather poetic description about it. It's always better accompanied by music. The art of changing the physical world for the use and benefit of mankind. This is what we do as engineers, and it's what architects do as well. And these words are carefully chosen because it's a physical, architecture and engineering operate in the physical world, but they fundamentally affect everybody. That's the purpose of what we're trying to do. It's what we're grappling with in any given age does change. So again, a little short extract. There won't be too many of these. He was Prime Minister in 1929 before the last recession, or last depression, rather.
First and foremost, there is the threat of an ever overhanging poverty. The nation is rich. Billions of pounds are squandered every year in deteriorating luxury, which blesses and benefits no one. Many who have not earned their possessions. Multitudes who have not have toiled all their days, and at the end are no better off than when they began.
That was a Scottish Prime Minister in 1929. I mean, saying that everybody toils all their days, we've got surrounded by luxury, and we're in a big pickle. And basically, 80 years on, we're still in the same situation. And what worries us changes from time to time, and how we deal with it depends on what we've come across during our lives. So where do engineers come from? And I could say, where do architects come from? Where do you come from? Where do people come from? When I was at Imperial, they actually thought that I was from another planet, which is well, it either says, I took that as a great compliment to the other planet, to be perfectly honest. But I'm going to show you a few pictures of my own life, just very quickly, just to show that it's an ordinary thing, and everybody has this equivalent set of pictures. But what you do as you go through your upbringing, who looks after you, what you work on, what you do for your hobbies, trying to, all this sort of stuff. It's all part of what makes you, and that's what you bring. Every time you try and design something, you bring playing the guitar, playing rugby, in my case, or whatever, you bring your particular take on it. And, of course, you interact with other people who bring their own take on it, and that's what happens when you're in a design team designing a project. And the more sort of directed your experience, you would think, the better you would be at designing stuff. But actually, well, in my experience, it's people who have nothing, who in their sort of non-working lives do things which have nothing to do with their architectural or engineering work, who tend to come up with the most interesting propositions because they have a better understanding of what human beings need and what the world needs. They have a broader experience, and so the solutions tend to be quite rich. Also, as Will said, we started 10 years ago. I left Arabs, where I've been working for 20 years or so, and we started this practice in a kitchen. Then in a spare bedroom. We won £1 million fee from this spare bedroom. It's quite an experimental practice, and it's very adventurous in terms of the way that it's set itself up. Tim Harris, who's sitting in the corner there, was our first employee, and he's actually foolishly come along to listen to this as well. That's him, so you can see what happens to you if you work for us for 10 years, all your hair falls out. And he holds the record for coming to the most lectures I've ever given. And now we have a very nice office in Regent Street, about 50 people. We've never had to borrow a penny, and we've just converted ourselves to a trust. So what we're doing now is we've given the practice It's worth about £5 or £6 million of 50-strong practice. We've given it to the employees. So it's become a trust. And the reason we've done that is because we want the employees, we don't want to cash in, because for us to cash in, but still effectively to be dependent on other people's work, to me is a little bit, you want a good bunch of people working for in the end, for their own satisfaction, because the more they can get out of it, the more they'll put into it, and hopefully the better the projects have been. So we've converted ourselves to a trust, which is called the Useful Simple Trust. It's been going for 2 months now. Now, you might be an engineer, you might be an architect, you might be a designer. You can substitute any of that word for any of those three. So I'm going to give you a little test. I'm not going to say, are you an architect, or are you, I don't know, a civil engineer, or are you a fashion designer. I want to find out a bit more fundamentally. Well, it'd be helpful if you could find out a little bit more fundamentally what you're at. So we're going to do a little tiny test for which you need it's 10 multiple choice questions. Very, very easy. All you need is a sheet of paper and a pencil, which you can write A, B, or C 10 times. That's all you've got to do. If you haven't got one, borrow one from a neighbor. This test, just by way of explanation, this came out of a summer school that I run with Ed McCann, who's my partner for the Royal Designers, for the RSA. And it has designers from, fashion, aviation, shoes, graphics, all sorts of stuff. But we could see a bunch of characteristics coming out of people which were nothing to do with what they did for a living, but it was much more about what they were as persons and what made them good at particular bits of design, maybe struggling in other areas. Okay, everybody ready? Just answer the questions. Very simple. Okay, walking down a high street, when you come across a pocket watch on the pavement, do you A, all you've got to do is write A, B, or C. Stop and look at it and wonder if its owner misses it. B, step on it. C, pick it up and shake it and see if you can fix it. Okay. Next question. You've been invited to a fancy dress party. Would you A, dress normally because people are more important than clothes? B, spend the 3 days before the party trying out everything in the wardrobe, then wear a sheet? C, hire the costume your friend wore last year? Next question. You're walking on a desert island and a coconut lands on your head. Do you A, pick it up and decide what to do with it in good time after proper reflection? B, throw it into the sea and then dive in after it? C, open it with a penknife, you always carry it in your rucksack, drink the juice, eat the flesh, and make some castanets? These are, by the way, these are real answers from real people to these questions. Your hose pipe in your garden has become knotted on the reel. Do you A, go to the shops and buy another one because this is cost and time effective? B, prick holes in it? C, spend the afternoon untangling it? Next question. A friend is in big trouble and asks you to lend her £1,000. Do you A, explore whether she really needs the money or be better off with another approach? B, lend her £10 and suggest she goes to the races? Or C, check your statement, write a check agreeing a reasonable rate of interest and a repayment schedule? Next question. You're invited to be the first person on Mars. Do you say A, what's the point of space exploration? B, yes, and may I bring my hat? C, no thanks, I'll let somebody else go. Next question. You're only allowed to take one book on holiday. Do you take A, the Oxford Dictionary of Quotations, B, a ball, C, the SAS Guide to Survival? Next question. There are 3 of you floating in a life raft. There's only enough food and water for 2. Do you A, carefully consider the 2 who would make the greatest contribution to civilization on the return, and then brief the 3rd on how to achieve that desirable outcome? B, rock the boat. C, eat the bloke who wore the sheet to the party? It's raining and you discover you have a hole in your shoe. Do you A, ask yourself whether it's worth making the journey, and if so, choose the driest possible route? B, walk right through the puddles and try to get the water inside your socks to warm up? Or C, hop? And the last one, you're holding a dinner party and you find you've lost your recipe book. Do you A, phone for a takeaway and ask them to deliver one course every hour so there's time to talk? B, use whatever is in the fridge. What is a recipe book anyway? Or C, go round to your next door neighbor and borrow their recipe book. Okay? Oh, now, all you've got to do is just add up the number of A's, B's, or C's. As this is an architecture school, I'll give you a bit longer. Now I'd like you to do a master plan for those questions. No. Okay, who was mainly A? Put your hand up if you were mainly A. Who was mainly B? Mainly C? That's interesting. So a reasonable. So I think most C's, next were B's, quite a few A's actually. Okay, so what we've done is we've characterized the sort of people who pick these questions. If you answered mainly A, you were a philosopher. Mainly B, you're an artist. Mainly C, you're an artisan. And these are very useful characteristics for people who work in architecture and engineering, because actually you need all three of them on any project. You can't do any of them on your own. You can be an artist and do art on your own, but you can't do buildings and architecture on your own. And the philosopher, there's a philosopher, tends to write stuff down, think of things in great detail. We won the Velodrome competition for 2012. That's one of the projects we were working on with Hopkins. And Chris Hoy, who's just won all those gold medals at the Olympics, he responded to this written statement about what we're going to do, which came from a philosopher on our team, a guy who was sitting there with his head on his hand on his chin. And the philosopher is what characterizes philosophy in terms of you need to have the whole picture, basically. You need perfection. And you need to understand why you're doing what you're doing. So this starting point is extremely important. And you can see the whole thing, and you can actually see the end very often. Tends to get a bit more blurry, actually, from that side to this side. But anyway, you find it, and philosophers find it very hard to start without the whole picture. That guy with his, who sits like this cannot do, if you give him a blank sheet of paper and say, design me a library building, he just simply can't do it, because he's an engineer. But even if he was an architect, he'd find it very hard, because he have to imagine what's the purpose of a library, and go right into the sort of intrinsic qualities of a library before he can even start moving. It takes a very long time. It's very painful. The artist, as it happens, those were my answers for the artist. And the artist sketches, or just imagines stuff. And is very unprecious about, you're perfectly prepared to screw it up and throw it in the bin. Norman Foster is an artist in that context. He's not precious in the slightest. But sometimes they turn into fantastic projects. But the journey of an artist through a project, if you were an artist, this is the way, you may recognize this is the way you do stuff. You start from here, everybody's expecting you to go over there. After a little while, something more interesting comes along, so you change direction, and then you may go back on yourself, and you go all over the place. You can go disappear up your own profundament quite often. But you often end up in a very funny place over here, which nobody ever thought of. And it's characterized by lots of responsiveness to external influences. And you find it very easy to start, or to change, or to start again. Actually very hard to stop, and yet you often don't even know when you reach the end. The artisan, this is an artisan in our office, surrounded by books, complicated computer programs, the handbook of pile testing. He's actually got it on his computer. He's very, very sad. But anyway, no, he's a very talented man. Very, very, should be more wealthy than he is. But what he tries to do, if he's an architect, he would concentrate on doing the perfect handrail, or the perfect stair riser drawing or something. Or maybe the perfect heart diagram, you know, these horrible traditional architectural things where, the sort of quintessential thing, and it would be based on what everybody's been done before. He would just absorb thousands and thousands and thousands of previous incarnations of whatever it is he or she is trying to do, and then try and produce the perfect version. So for an engineer, this is a sort of, it looks very boring, but the perfect reinforced concrete drawing is something that an artisan would try to do. And they keep on doing it. And the journey of an artisan starts with everything that's ever been done before and tries very hard not to get over here, which is the area where nothing has ever been done. And what they do is they incrementally try and move this line forward, just a fraction based on everything that's ever been done before. So if you answered as an artisan, now an artisan actually has a very important sort of reality check purpose. You know, they say it's been done before, it's possible, it can be done, and we can move it, we can do this, and we can do this. Actually, sometimes finds it very hard to start without having somebody else's concept to work from. So if you put yourself down as an artisan, you may recognize that in yourself. Many people, of course, have bits of everything. So, you can be different colors. You can mix up in a team. The team sort of mixes up in different ways with different proportions, and they play off each other. In the world we operate in, of course, we're not called any of that stuff. It would be helpful if we were just called artisans. We're actually called engineers, designers, architects. We have all these titles. There are people out there who, voters, users, people who use the stuff that we design, who are very, very important. But actually, all of that is extremely unhelpful. I mean, to give yourself a label, I think, is very, very restrictive. Extremely. I mean, basically, we're all designing stuff. In the end, well, it's voters, but they're the people who commission us to do the projects we're working on. They vote for our talents or lack of. So what is, if we're all designers, what is design? I mentioned that little test, the artist, the artisan, philosopher, came out of the Raw Designers Summer School. I mean, these are recognizably bits of design. These are all done by raw designers, one sort or another. And some of them are very familiar. But the way that people design things turns out to be the same all the way through. And again, it's handy to know this, which is design is this bit in the middle here, and it starts from somebody somewhere says, I need something, and at the end, there's somebody who says, I'm going to use something. In the middle, there's this process where people say, right, I'm a really good architect or a really good engineer, I have lots of ideas. But actually, just having ideas isn't much use. You've got to be able to know whether they're going to work. And somebody somewhere has got to build in all the thousands of variables on a project, all the different things which impact on a project, and make some sort of judgment as to whether or not that is the thing that you're going to go with. It doesn't matter how good your idea is if it fails the first test or the second test. And I give an example of the Millennium Bridge, which was a project I was responsible for when I was at Arups, the Wobbly Bridge. And many people have said to me that the Wobbly Bridge was a failure of mathematics, which is a failure of testing in here. And actually, every single sum that was done on the Millennium Bridge was done properly. They're all perfect. It was a failure of conception. We failed to conceive the right set of tests, and so we didn't do the test. We didn't conceive the test for that particular phenomenon where people walk all together and lock themselves into the movement of the bridge. So it hadn't been seen before, and we weren't sufficiently artistic to invent it. So the judgment that we made out of this imperfect set of conceived tests was a perfect judgment on the wrong set of tests, as a result of which, when we made it and used it, it didn't work. As a result of which you learn, next time somebody asks for a bridge, you can build on that experience and go through it. So there are people who are very good at having ideas. There are people who are very good at testing. There are people who are very good at assembling lots of complicated things and judging them. And you, again, if you're trying to, well, if we are all trying to work out how to approach design work, it's good to be honest with yourself and try to work out which of these bits you're good at. And if the bits that you're not good at, find somebody who is good at it and put them next to you and spend a lot of time talking to them and work together. The engineer's role traditionally sort of sits here. Although if you ask Brunel, he would go up here when he's dealing with railways. So it's shifted a lot in the last 100 years or so. In terms of judgment, there's another little thing about. Just go back to that previous slide. Thing about these tests is woe betide anybody who invents a test and then says, if I follow that test and I make a judgment based on it, it's absolutely going to work. So people tend to be very conservative when they do these tests. But that's a relatively recent phenomenon. So engineers are always asked, have they over-designed things? Where's the massive factor of safety in it? And we can't do what we want to do because you oversize the columns, the beams are too heavy, the whole thing's going to fall down. You make it far too hard for us. Now, it wasn't always like that. And again, in another one of these little programs with the BBC, we built the biggest weapon the Romans ever had was a thing called it was a catapult that weighed 23 tons made out of oak, which was it was used in the siege of Jericho, amongst other things. And it was designed to fire a 60-pound ball, rock, about 100 meters or so, because that was the out of range of the defenders. So we were asked to reconstruct this thing, and we designed it according to modern calculations, but using Vitruvius's dimensions, because he explicitly writes them down. And as a result of that, we proved that it wouldn't work, but we built it anyway, and then tried to find out what would happen.
That was awesome. Came flying out. He's been there a long time, 67 feet, and that was the first shot.
Oh, very impressive in the right direction, actually. And I'm now just kind of calculating to see whether my initial back is right.
We're actually trying to go to hit that white and
Oh! That's a ball thing, yeah, first shot since Roman times, it worked.
Although everyone's happy it's fired, the truth is they failed their challenge. The Romans used to hit the walls. The team hasn't. They decide to have another go. If they tighten up the ropes, the catapult should have more power. But then Chris spots some damage.
What are you looking at? What are you seeing? We've got some fairly, by modern standards, fairly gigantic cracks in the outside stanchions. It comes right down on the line of the notch.
See that these things, if you saw that in a modern structure, people would say, "I'm sorry, you failed. We're going to sue you. It's going to be disastrous, and it's all going to go horribly wrong." The architect would not recover. The engineers would who have the biggest insurance premium, insurance policy would end up holding the baby pocket. And rightly so in many ways. But the Romans, of course, all they did, they saw a crack like that, and they just put a piece of steel around or iron around, wrapped a piece of iron around it, or made the wood thicker. They just, by trial and error, incrementally, through experience, they made them bigger and bigger and bigger.
It's as if somebody's taken a chainsaw and just sawn straight down it. Yeah? So I'm going to wind the load up a little bit more.
It's quite a big...
But I think everybody should just stand clear while we're doing that. Great. What do you think? I think you should. Really? Yeah.
So they start pumping up the jacks. But the catapult's already so damaged, they know this is their last chance.
Now we've just got to go for it. Everybody stand well back and we'll go for broke. And either the machine will break or hopefully we'll hit the wall.
So that the arms can be pulled right back for maximum power, they're taking the braces off and replacing them with cables slung underneath.
Okay, Ian, Steve and Dennis can go. Correct. I think you need to impress upon people the need to get the hell out of here this time.
Can we just keep going right back? Sorry. So much load in this thing. If that goes anywhere, there'll be bits of timber flying all over the place.
Okay. Yeah, we've got pulling. Don't want pulling.
Okay, take tension. Gently. Okay, up to 3. 3, 2, 1.
All right. hit the ground smooth, and yeah, Caroline Reagan won it. Oh, that was incredible. Bloody hell. Look at that, eh?
30 yards and 1 foot. It was 90.3, so that means 9 foot.
And that's because nowadays we have to design these things virtually. So you're trying to do it in the computer. You don't often get a chance to do trial and error, but it's very, very important. You know, knowing that was overstressed, by modern standards, overstressed to four times what the conventional modern set of codes of practice would allow you to build to, and it still worked, or almost worked. So we're in this, I'm sure you've seen this many times, but we're in a time of great change, or all of the experience that we built up over the last 2,000 years or so is actually may not be much use to us going forward. And Darwin put his finger on it by saying it's not the strongest of the species that survive, nor the most. It doesn't matter how bright you are, but if the environment you're in changes, you've got to change. And the environment we're in has changed. You know, we haven't got enough energy for the people on the planet. We have too many people on the planet, arguably. We have rich and poor, all sorts of other things, which are major, major global forces. When you come down to designing buildings, designing towns, designing communities, they're very important subsets of a much bigger thing. And the ability to change the whole lot is very important. That's where we are all in this moment where we have to change. And it comes partly from the pace of change of technology that I showed you earlier. So, I mean, and of course it's very, the building world, you know, still working, I don't suppose you teach Palladio here, but I mean, basically everybody still, in many schools, people still study the classical orders, and it has a sort of magical, there was a conversation in the bar earlier about the Fibonacci series and how fantastic Cecil Baumund is. You know, really, I'm sorry, I just think there are slightly bigger questions around about whether or not you know the Fibonacci series or not. And I mean, one of the things that we're trying to work with now is, this is a project with Richard Rogers for an underground station in Naples. There's a big hole in the ground, trains come in here, and you're trying to get out at the top. And we're trying to, and a number of people are doing this now, trying to evolve our projects, not so they just look pretty, but so that they actually work in a way which is adapted to best suit its environment. So it's Darwinian evolution of projects. I mean, to give you, so this little canopy, it's hard to do it on a whole building. It's really, really difficult, and there aren't any examples of it yet. But you can do it on little pieces. So this canopy, which I say is little, it's about 70 meters across. It's nearly a football field long. But it's basically a gigantic sunshade, rain screen. But there are bits of this, because this is a very deep hole. If you just shade all the sun, it's very dark at the bottom of the hole. So what you want to do is let the light in where you can, and stop the light coming in where people are walking. So what we've done, there's a guy called Fred Labbe in our office who started off designing water systems, rivers and drains and that sort of stuff. Has a very good understanding of the natural world, and he's developed and very good at using spreadsheets, and he's a sort of all-round computer person, but he does sculpture in his bed. I mean, he's a very broad character. He developed a little digital algorithm process, which is a bit like it's a little bit like the work that's being done. I don't know if you do it here, but at the Architectural Association, they have Mike Weinstock runs a course called Emergent Technology, where I've been the external examiner for a while. And in this methodology, you allow the project to grow itself in response to its environment. So it's hands-off, basically. So I mean, just show you an example. You will have seen these things, but we're attempting to do a buildable version of what has been, by and large, so far, just a theoretical exercise. So this is and it's designed. This system is designed to get the sun down to the bottom of the hole, stop the sun getting onto the people who are walking around, and it's mapped through the whole year's climate. Minimize the amount of material, minimize the number of components. I think there's one other driver, which I've forgotten now. It maps to the flow of the people with direction through to the entrance. And it basically evolves. So here, you can just see emerging bits of open system. That's where that allows light down to the bottom of the hole. This part here has evolved itself. And if you do a proof and you study it as a scientist, you can actually prove that that is the optimum configuration for all of those things. You know, it's converged after 70 generations. And the way this works is it actually, you engineer one solution in response to that given set, and lots and lots and lots of other solutions. Then you test them against whatever it is like how much sun is getting in. And the two most successful ones, you allow them to mate. So they go and shag each other. Big roots, they shag each other. And their offspring are the next iteration. They have the characteristics of the two best of that given generation. And then they go and proliferate. And from time to time, you put in a random mutation, just like nature does, in the hope that you're going to jump into a slightly different evolutionary path. And you end up with a very effective design tool. So, you know, it's in its infancy, it's coming. Lots of other people are having a go at this as well. But I mean, to actually get it to the point where it's usable is, well, it's still to be achieved in reality. I mean, the proof is in the sum path diagrams and all sorts of things which you can test. There are simpler ways of dealing with some of the big questions, like what do we do about resources? I mean, one of the things you can do about resources, you can reuse the buildings that you've already got, reuse the cities you've already got, which is very unfashionable. Most people want to do new stuff, but actually it's it's challenging and very important. And we did another project with Rogers. This is for the old bull ring in Barcelona. This is with all these projects are with our current practice with Expedition, which has been derelict for 25 years. The Catalan people don't like bullfighting anymore, apparently. And so the question was what to do with it. It's a very iconic project. I mean, Mies 1929 Pavilion is just up there, literally, just where my tip of my finger is. It's very important. And every Barcelona person comes past this site on the way in and out of the city. So to knock it down, I mean, for a developer, there's a big, nice square site on a very important intersection. It was worth a fortune for office building. But actually, for the people of Barcelona, that wasn't enough. So in the end, with Rogers, the decision was made to refurbish it. Now, the thing that they like in Barcelona is shopping. They don't like bullfighting, but they do like shopping. And they like going to restaurants and bars, and they do like entertainment. So this covers all of those things. So it has shopping, entertainment, restaurants, bars, a whole lot. On the top here is this UFO-shaped thing. Is a theatre for 3,000 people, which is you can do what you like on. And then the cinemas, restaurants, shops, and everything else sit inside the old bull ring, and actually in the ground as well. This is an engineering sketch. I did this with Laurie Abbott, who many of you may have heard of if you haven't. He's a fantastically talented architect who used to work for Richard. It's his last project. I mean, I hope this is just coming to fruition now. So to keep these things going as engineers, it's a hell of a job to hold up an old bull ring while you're trying to convert it like this. So this is all temporary, all this stuff on the outside. But basically, it was completely ripped away. The hill that it was sitting on was pulled down by 5 meters, and the building was left where it was. So you walk in from the street, because otherwise you have to go uphill, and people in Barcelona don't like walking uphill. Gigantic hole dug underneath, a combination of all the normal services. These sort of heroic pieces of steelwork, there's another one around there, just work their way around. So the old ground level was up there. This is the new ground level. And you come in between these through into the space. This is engineering gymnastics at mega scale. And then on the inside, we built, it's finished now, a deck which doesn't touch the sides. The old walls are out here. There's a gap. And this deck is the floor of it's the roof of the shopping area, but doesn't touch it. So it's more like a cover, but it's the floor of the performance space on the top, which is covered by a big timber grid shell. This is it as of about 3 or 4 weeks ago. So, and eventually, all this lot gets taken down, and you're just left with the bull ring. Now that's a mega refurb. You know, it relies a lot on engineering conjuring, but a very strong understanding of how these things work. You can't afford to drop the bull ring while you're trying to change its use. That would be a bad thing to do. And there are massive benefits in terms of the environment in reusing buildings. And around the corner here, you've probably seen this project which we've just finished with Make, Ken Shuttleworth, at Baker Street. In fact, this your project, no, not quite on here. But this project converts the old Marks and Spencer's building into offices and apartments, and again it's characterized by bits of engineering conjuring, bits of architectural frilliness, if you like. But the crucial thing about that project, by not knocking it down, firstly it was faster, so it was actually let before the recession bit, which meant the client's very happy because there's loads and loads they can make loads of money out of it. It saves the amount, by not knocking down the old concrete frame, the waste produced by 100,000 people in a year. It saves enough energy to run 8,000 homes for a year, and it saves the equivalent of 4,000 family cars running on the roads for a year. And I think it's important. I mean, that's just one building, but if you imagine doing lots and lots and lots of buildings, it's a huge problem in our cities. You can't knock everything down and start again. And every time you knock it down, you lose all that potential benefit. And I think it's a big, important area that needs to be much better handled, is how to deal with existing stock. Social values have changed. I mean, there's a guy at the RSA called Matthew Taylor, who's a sociologist, used to work for Tony Blair in Number 10. He runs the Royal Society of Arts, and he's into this thing called pro-social behavior, which is about everybody taking responsibility for their own futures, and not allowing governments or somebody who's artificially put in a position of seniority to necessarily make all the decisions. And so he's pushing for a very, very engaged society, which is arguably a very interesting change. It's not the first time it's happened. I mean, think about the French Revolution. But there have been changes. This guy, 3 or 4 months ago, he had built this house as a sustainable house out of more or less stuff that he'd found on the site. And it was, he was told by the local authority to knock it down. And they'd been running for 10 years to knock this house down and forcing him to knock it down. And he resisted and resisted and resisted and resisted and resisted. And after 10 years, he became Flavor of the Month, overnight success. And they changed the policy rules, and he was allowed to keep his house, and he got planning permission to build 8 more similar ones. So it has changed in 10 years. It's very important. Now, so another little, in the context of, I'll give you a clue, it's in context of the world we're currently occupying. I just want to ask you a little question. Which of these projects do you like the best? Who likes that one the best? Nobody. Who likes that one the best? A few people. Who likes that one the best? And who likes that one the best? Great. That's the Sydney Olympic Stadium. Nobody put their hands up for that. 2000. You don't have to read all these figures, but if you just remember it in terms of cups of tea, the amount of energy in the steel structure is equivalent to a cup of tea for 1.6 billion people. There's a quarter of the world's population can have a cup of tea in exchange for the steelwork. Who likes that project? Lots of people put your hands up for that. Okay. Same size stadium. 2.5 times the population of the planet, nearly, can have a cup of tea, rather than a quarter. There's nearly 10 times as much energy in that structure as there was in an equivalent sized stadium at Sydney. So those of you who put your hands up and said you like that, okay, as a piece of art, maybe, as a piece of sculpture, maybe, but you have to ask yourself whether or not your judgment, whether the tests you were applying were sensible or not in the context of what's going on at the moment. Many, many people have said, well, actually, as a way of saying, stuff the 14 billion cups of tea is actually very good because it got China off the antiquated culture route into the 21st century at a stroke, and therefore, in terms of establishing China's place in the world, it was worth everybody having to sit down and drink 2.5 cups of tea. It was actually worth it.
Engineered in Britain by Arab.
Yeah. By actually, I believe somebody whose name was mentioned earlier. I can't bring myself to repeat it. This is another Arab project, actually, engineered by a very, very good engineer from Arabs. Do like this one, quite a lot of people. It's obviously smaller. This is about 17,000 people, but it's designed long-term for 6,000. Only enough cups of tea for less than 1 billion people to enjoy themselves. And this one, which is a velodrome, which is one of our projects, which we're doing with Michael Hopkins again. Same size, 6,000 people, only requires as much tea as 1/8 of a billion people. So if you compare it to the water cube, it's about 6 or 7 times more efficient in terms of energy. So if you were to mark them just in terms of energy in the structure, if you're an architect working with an engineer and they say, if you say as an architect, can I do a building like a bird's nest? And the engineer says, yes, you can. The answer is yes, you can, but be aware of the consequences. It's 10 times nearly less efficient than a simple, this is Steve Morley designed this one as an engineer in Sydney, a simple engineered stadium. And even the water cube, which many people say is a very graceful structure, it's a very elegant solution to the problem, is still 7 or 8 times for the same size building, 7 or 8 times more expensive in terms of energy.
But if you were God giving out cups of tea to the world, how would you rather give out 14 billion or 31
It's a question.
It's a tiny spurious argument.
No, it's not. The question is how much energy.
Oh, it's a bad analogy.
I think that's a very bad analogy because I'm not God. But if I was, I'm not moralizing. I'm just giving you some facts. No, I'm not. I'm giving you the facts. You're moralizing.
You're telling me that your building is moralizing.
I'm not. I have not used any. I'm very happy to debate this as long as you like, but you won't win. Honestly, I'm not. All I've done is given you facts. I haven't
I don't have a view about it, but I think 14 million cups of tea seem more generous than 0.125.
If everybody on the planet could have a cup of tea, you'd be right. But not everybody on the planet can have. If in exchange for that, you've got to take something away from somebody else. There simply isn't enough energy for everybody. We'll talk about it afterwards, and then we'll have a fight. Then we'll have a fight. If that doesn't work, yeah. On that, you're telling me you like that building.
No, I'm not.
Okay. All right. We'll stop moralising. If you were just doing it just in terms of energy, just using the facts, that gets on the traffic lights. That's red. It's very easy. The water cube, amber. And actually, in fact, the best project in terms of energy per person using it is the Sydney stadium. It's better than the velodrome. It's a bigger building. But they're both roughly green. And obviously, we're going to do much better. And you'd hope there would be a sort of white scheme that comes out that has nothing in it. But I'm not moralising, but I just want to point something out. This is another fact, and it's got to be fact because it came out of the paper. When the money started going berserk, I don't know if you know about Lord Turner. He was appointed as the chairman of the Climate Change Committee at the beginning of January this year, and after about 6 months, September, everything went pear-shaped in the finance sector. And he happened to be chairman of the Finance Services Authority at the same time. And so the government was forced to decide which of them he would run with. Have you got any guesses whether they went for climate change or money? Money, of course they did. It was too time-consuming to perform both jobs. So they took him away from doing climate change and they ran on to money. Now, arguably, that could be, on a moral basis, could be right. Might be the right decision because it's more important Who gives a monkey about climate change if there's no one here to enjoy it because there's been a war about oil, for example? So, I mean, these are hard decisions. I'm not pretending they're easy. Anyway, I'm going to get something easier now. Traditional design spans. And well, this isn't as simple as it seems. These 7 or 8 pictures I'm going to show you have something in common. Okay? There's the tar steps, Condugar, Iron Bridge, Menai Bridge, Clifton Bridge, Robert Maillard, Sydney Harbour Bridge, Humber Bridge. What they have in common is that the people who designed those bridges would never have been selected according to the RIBA's competition rules in this country. Because all bridges, well, certainly in terms of the RIBA's competitions, have been specified as having to be led by an architect. So none of those guys, Brunel, would not have been selected, which is a bit absurd, really, when you think about it. So we've been battling to get that changed, and we've got it changed at last. So the River Soar Bridge competition, which is out at the moment, is up for both. And to give you an example, and again, this is not moralising, I'm just stating a fact. This is a factual piece of paper we got from an architectural friend of ours, inviting us to participate on a bridge competition with it. I'll read it. I've come across this RIBA competition for a pedestrian bridge. While I have little or no experience of bridges, you guys should be able to put together a convincing few pages. This is for a competition that specifies the architect has to lead the team. 2 options if you're interested. You team up with an architect who has previous bridge building experience, or we submit together primarily on the basis of your previous experience and our fantastic working relationship. Let me know what you think. Well, that happens all the time, and luckily that's now changing. The only reason I put this up is I'm not knocking architects, I'm not knocking or saying engineers are pathetic. All I'm saying is it's just really, really unhelpful to have to put a label on somebody and call them architect, engineer, designer, or whatever. So the River Soar Bridge, which is out at the moment, if you want to go for it, architects or engineers can design it. There should be any designers with the right experience, really. Now, in terms of what we do, because it's shit when people do that to you, honestly. They piggyback your own experience. And what we do, I mean, as I said, I was responsible for the Millennium Bridge. The human beings, the whole talk is about humans, really, do funny stuff. And apart from getting the bridge to wobble, they do other things as well. This is the world space hopping record attempt, where they knew it could get it wobbling sideways, but they decided they would all sit on top of it and bounce up and down. They had 800 people on space hoppers all bouncing up vertically at the same time. That's fantastic. When you design these things, you never have the faintest idea that somebody's going to do that. And projects come from the funniest places. So we're working on a bridge, which I'm just going to show you in a second, which was originally started by Margaret Thatcher. When she went up to Stockton-on-Tees, which is the 2nd poorest town in the country, next to the poorest one, which is Darlington, and said, oh, these poor people, they haven't got anything, they haven't got a pot to piss in. And said, oh, I don't know what I'm going to do. And instead of sort of doing her photo shoot and then going home again, the local people stood up and collared her and said, oi, do something about it, really do something. And on the way back, more or less, she decided she better had, otherwise all the people up there were just not going to vote for her in a million years, ever. And so they started putting money in. The University of Durham has a annex. They started cleaning up the land. It's been going on for a long time. This is the river, shot from the University of Durham site onto the old chemical works on the other side. And they ran a competition, the RIBA ran a competition, architect-led competition. And so we paired up with an architect, because we were forced to, very nice man, and did a series of pieces of work. Now the thing about bridges is that when they get beyond, I don't know, 20 meters or something, they get out of the realms of stuff that you can guess the answer, and rapidly into the world where nature does something horrible and starts, we found on the Millennium Bridge, starts going wrong, and actually really big-scale bridges of any sort. The world is littered with bridges that have fallen down. You've all seen Tacoma Narrows fall down, Millennium Bridge wobble. So it becomes a point where you can draw. I mean, it's possible to draw this diagram. It will be impossible to build what's on those drawings unless you're an engineer, or design something that could be built unless you're an engineer. So there's a big distinction. In the same way that if it was a building, and people come at it with a lot of experience of how people use buildings, if an architect draws a sketch, buried in that sketch is lots of intrinsic understanding about what that sketch would actually mean if it was turned into a real building. And that's very important on buildings. On bridges, it's very important that the intrinsic understanding that goes into a sketch like that, onto a single line, is something that is well understood at the time that you go for the competition. Because if you win, and you can't get it to stand up, you're in serious trouble. And this form of shorthand, of sketching shorthand, engineering sketching shorthand, has been around for many, many years. But Leonardo da Vinci, in his codices, did a series of very, very simple engineering drawings of a way, in a language that, even though I can't read Leonardo's mirror writing, I can read his engineering sketches. They're exactly the same as the ones we use. So a stick represents a beam. Another, an arrow represents a force going in a particular direction. The language is, now whether he developed it or not, I don't know, but whoops, somebody wiser than I will tell me. But we still use that language. And so if you're doing a sketch like that, you have to know, and those were done on the train on the way back from that first site visit, you have to know that you can get the thing working. And you start with very simple things. This is some toilet chain hanging up in the office. And then they voted in the pubs in Stockton and the nightclubs. So on a Friday night, you could, if you had your beer on one of these beer mats, you could turn it over and there's a number on. You could phone in with your vote. And I must say, actually, you can tell actually by my tone of voice, I'm slightly exercised by this whole question about, let's say, putting the right people in the right place to be able to do things that they have some capability in. As I say, there's a distinction on the sort of project that you're working on. But I was in Selfridges, and there was a press launch. Remember, we had a new practice, been running for 3 years or 4 years. We entered this competition, we were in the last few, and they announced that the bridge had won that we were working on. And it was very important to our practice to be properly involved in it. And actually, because it was our concept, it was important that we ran the project as well. It was way beyond as an engineering project, really, even though it was a piece of architecture and a piece of sculpture. But the bridge was designed by the architect with support from the structural engineers. And I was in Selfridges when I got this message on my phone. And I was trying to buy a radio, and I ended up buying a much more expensive radio than the one I actually meant to buy, because I was so bloody angry. I was walking up and down steaming. How dare they say the architect designed the bridge? Don't they realize that they're killing an entire generation of engineering students who will think that the architect designs stuff that the engineers never do? And you actually need both to play their part on most projects. So I bought myself a much more expensive radio, that's it, than I actually meant to. And even worse, then they changed from analog to digital, and so it's now useless. There's a £300 radio blown away just because I was so angry. Anyway, we built it at small scale in our student projects that we do. We're still doing with Imperial at the construction area in Norfolk. Tested it in the wind tunnel, tested its wobbliness, having learned from the Millennium Bridge. So this time, the conception of the tests included this test, which we didn't do on the Millennium Bridge, and nor did any other bridge designers. Constructed it as a kit, which we learnt from Norman Foster mainly, Richard Rogers a little bit, Renzo Piano a little bit, but mainly from Norman, who, as I say, is a very, very good assembly type engineer. And then it got built. So these little pieces, I mean, these pieces, to give you an idea of the scale, these little pieces in here are these. So you start to, this little dot. And this project was drawn in 3D, more or less, from the off, because you can't do it in 2D. It's too complicated geometrically. So that little dot in the middle is this piece. I mean, the forces going through here are colossal. There's Tim again. It's in Cleveland's workshop. So what started off as a single line has ended up in these great big pieces of steelwork. Where they hit the end, you have this sort of thrust frame. The deck on the Millennium Bridge, the cross-section of the Millennium Bridge has about 10 or 12 different components on it, including a piece on the edge which shapes the nose, so like an aeroplane wing, so that you don't get aerodynamic problems. It's a deliberate form. On Stockton, we didn't have the money to do that, and actually we wanted to be simpler, so it's split right down. This is the cross-section, so that the whole deck is cast as one piece. All of the drainage, the aerodynamics, the structure, the form, hopefully the beauty of it, all comes out of this one piece of cast concrete. And they're match cast. This one is cast against the one next to it. So that's a perfect join. And these little brackets are clamped on. I say little, I mean they're gigantic, really. And they're lifted into position off these cables, which are miraculously hung up in the air. You gradually work your way through. Now I just briefly mention, I mean, one of the things that is, there's a fantastic shot of Brunel's bridge at Saltash being built in 1850 odd. And at that time, they didn't have computers, they didn't have anything. They couldn't test these things apart from loading it up. So they built this bridge section on the riverbanks, and then to simulate a train, they put 1,000 tons of ballast on here and measured how far it went in the middle. And if it went down 5 3/4 inches, they thought that was in line with their very simple calculations. And if it didn't, they were in real trouble. They had to stiffen it or strengthen it and to sort of do a Roman strengthening job. And then lifted it into position. And this, they floated it out and then jacked it up. It's a fantastic project. And so when we were doing this, there's a slight echo of it, because there's our first part of our bridge, and this longer span was built on the bank, but instead of floating it out, it was lifted out, because technology has shifted a bit since 150 years ago. So it's just lifted into position using the biggest crane in the country, wasn't it? On a very rainy day. So implicit in that sketch was some sort of understanding of how you might build the thing, which again is very important. There's lots of photographs of Tim. Big cables, Millennium Bridge type cables. Where it lands at the end, it lands on a single pin. Now this is Tim standing at the end of the main arch, which is 120 football pitch and a bit. And that's standing in the middle looking back. You can see it's extremely slender. Now we couldn't have, it would have been impossible to do this. I mean, it looks like a fake, this photograph, but it's taken with a 50mm, equivalent of 50mm lens. It's just no way you could have done this even 10 years ago, I don't think. The technology has moved on a long way. But it's traditional structural engineering of as a sort of extreme version of it. I mean, the point I would make about this, we're all extremely proud of this project. It's fantastic to win the competition. It's fantastic to do it. It's a fantastic thing, hopefully, to make the people in Stockton feel slightly better than the second poorest town in the country because they've got this beautiful thing. But, and it's a piece of engineering art, I suppose. But really, in terms of the big questions that are out there, I don't think it's the future. And people still want these beautiful things, but really, for me, it's only one factor, one facet. And what you really want to do is you want to get the same degree of refinement into a much broader, more complicated questions. That's where we're going to have to go in the next 20, 30 years. And it's a cool thing, but even down to the lights, which we did with Spears and Major, when you walk past on the lights, it's taken such a long time to build this bridge, or to, it's 2003, the competition, I think. We couldn't do this, but the lighting technology has moved on. When you walk past, the light changes from blue to white, and then back to blue again. So you get trailed with a line of white light as you walk along the bridge. Probably lasts about 5 seconds, will be nicked by all the locals. Last thing. The last thing is to do with education, very briefly, and it's to do with how you get a generation of people to engage with the physical world, with human beings, with each other, from an education system which is being geared around in our world, engineering science, and in the architectural community, in some areas, and I'm sure this place is not an example of it, actually a very artistic background. And in fact, the reality is you've got to be somewhere in the middle to be able to do really, lasting projects that people can use. So in terms of education, one of the things that was never done, despite the fact that engineers spend all their time dealing with the physical world, one of the things that was never done was feeling how heavy things are. So if you pick anything up, it's extremely heavy. It was done as a series of numbers and pieces of mathematics. Concrete, steel, timber, these bits of stuff across here are exceptionally heavy, unbelievably heavy. And you have no idea, if you just do it all theoretically, that that's what they weigh. So we set up an educational proposition with Imperial, which involves industry through contractors, designers, and the students, and got them to build stuff. It's hard in the current, it's only because you could have real contractors working on real sites that we got them to do that. But, and I was a professor at Imperial, and many people have asked, professor of what? Because I have no research background. I was a design professor, but in the end, we realized that the design was absolutely pointless without understanding physical stuff. And so we constructed this thing called the Constructionarium, which I'm going to show you. We started with one, and now there are 17 universities. So nearly half of all the engineering schools in the country are doing this. We would love it if an architectural school took it on. So they all get a chance to study themselves in a physical background, working with real cranes, real steel, real people. And they build this stuff over the course of about a week. Actually, that's stopped. You may not realize that's a dam. There's a little bridge. It's very scary when you get given a pile of cables and you get told to turn it into a stadium or a bunch of concrete and told to float it out into. This is a hollow concrete oil rig. They built in a dry dock and just floated out. The difference between this and going on site is that you do it yourself. It's a very controlled environment for Gertie. Sort of. It's one of our little projects in Naples. That's the Neo Viaduct, I'm sure you recognise. This is one of our Naples projects. Now, the thing about these is, I think it's very scary if people are coming out of college. If people come out of college not understanding. Before we did this, people would come out of college having done a theoretical training and then allowed to design stuff for the real world without ever having come in contact with it in a million years. And in architecture school, it's very good because you have an awful lot of visiting practitioners who give you, I hope, some practical understanding of what the implications are of what you're designing. But in engineering school, it doesn't happen, and these are the people who you have to work with. You're going to trust these guys to tell you what's possible and what's not possible. So I'm hoping we shifted it forward a bit by doing this. That's the little Arab bridge. Anyway, and with that slightly cantankerous ending, that's the end. What I've been trying to say. What I've been trying to say is I use Stockton as an example of a piece of traditional, beautiful engineering, hopefully, that I think is almost past its sell-by date. I mean, the world doesn't need that stuff anymore. We're after something which is much broader, much more integrated. And I think the key to it is in that guy Matthew Taylor, with his pro-social behaviour. It's a slightly funny political thing, and as I say, it came from number 10 Downing Street. But he may have put his finger on it without realising it, because in the end, the people who ought to be designing the stuff that we're providing for them are probably the people who are using it. And somehow we've got to figure out a way of joining ourselves together without any titles, without any badges, get rid of all this historical baggage, and turn ourselves into people who can actually respond to those users, which we're going to include ourselves. Blah, blah. Thank you.
Thank you very much.
Yeah, if anybody's got any energy.
I can't formulate it. Sorry, what? Anyone else?
Anybody except people at the front? Yeah, sure.
What did Cecil Bowker do to offend you?
It wasn't excessive about what
Do you want? The honest answer is he called himself a designer. And when I knew him, which was until 10 years ago, he was never a designer. He was always a theoretical person and a very good business. Fantastic. And actually very, very good at his job. But he didn't seem to do design. So I just don't think the secret of the universe resides in the Fibonacci's. Well, maybe it does actually reside in the Fibonacci's truth. They're not the secret of architecture. I think if you want a building that looks like a snail shell, you can go and find a client who's a snail.
Go back to the genetic algorithm.
Yeah.
Darwin's thing. That what you ran there was optimizing to make that roof.
No, it's a breeding program.
It's a breeding. Yeah, I know how they work. But the you're feeding in variables, and in the end, it's looking for a solution. Is that correct?
It's what it does is it makes every single possible, basically every single possible solution within a given set of parameters, and then tests them.
That's my point. Is there another stage to that? Because in the end, you're ending up with a fixed object.
Yeah,
so
there are those stages.
No, what I mean, the parameters, whatever they are, in the end, it's not adaptable.
No, I mean,
so there's another layer, isn't there?
Yeah. That's what we're trying to do there. I mean, Mike's course, the AA, emergent technology, is fantastic, and it's pushing boundaries along ways, integrating all of the physics and the community and the form generation and all that sort of thing together. But it's not practical to build any of the things that's coming out of that master's course. What we've tried to do is to go back one and say, right, it's really important to get something built somewhere. So we've taken it down to the simplest number of variables. And we've conditioned, it's heavily conditioned. So the Pringle shape is already conditioned as a form which works in many other ways. So if it was a truly evolutionary process, it would actually test lots and lots of different forms, invent lots of them. Some of them would randomly mutate. Then most of them would die because there would be something else that was best suited to the environment.
But it would also change in real time.
It would. And I think that no, you're absolutely right. I mean, what we've tried to do there is a first step experiment, but we're really seriously trying to get it into the real world and build it, so that people can go to it and they can learn from it. And I'd say it's not trivial. It's the whole of the new Naples Underground line, so lots of people go through that near the station, and with a very well-known architect involved as well. So, Rogers. So I think it's important somehow. It's just that I'm also, just to give you an example, to run the conversions, I think Fred was running in 11 hours, all machines hooked together, took 11 hours to converge just with that. very heavily constrained problem. So imagine trying to do it on a building or a whole project, or give it becomes a really unwieldy design tool. So, I mean, you can see the future, but you can't get to it yet. But I hope that we'll do that. By the time we've done it, the technology will shift. And of course, the thing about it is it's not, there's an awful lot of human judgment kicking around in there about whether you like what's coming out of it. And if you like it, you might decide to push it. If you don't like it, you say, oh, actually, it's too much effort, we won't go for it. But so there's a lot of subjectivity. It's not truly Darwinian, but it's part of the way there, and we're using it as an example of the process is purely Darwinian. It's much too heavily conditioned. It's like the turtles, or the tortoises, you know, being evolving in a room this size where all their food is flung into them whenever they need it. You know, they're very. What's happening out there is nothing to do with their evolution. So but I still think it's a very interesting experiment. It's different from optimization. It's fundamentally different. I'll just take the one at the back there.
I do see the importance of not labelling individuals for personality traits like you're talking about, but I do think there's definitely a very important emphasis on labelling us as a profession, as architects, engineers. But we seem to be living in this world now where, you know, the successful guys seem to be the Foster's, this fusion of Foster's era of engineer architect. Do you think it's time for more of a joint study, a joint education between engineering and architecture?
Well, I mean, if I have I think it's just a big spectrum. The whole thing is a big spectrum, and I think that I can answer by giving you an example. I mean, BDSP and Patrick Atelier 10, and I think possibly Guy Battle as well. So, you know, 2 or 3 of the up-and-coming environmental practices came from Ted Happold's integrated school at Bath, where the engineers and the architects worked closely together. And at that time, there were no environmental engineers working on the design of buildings. And since that time, there haven't been, or to my knowledge, any significant players coming through who have that sort of integrated take on the world. So I think that it's a much lamented loss that Ted died, that the school at Bath isn't what it was. And many people have bits of integration, but I think that in the end, I think you've got to go upwards. The architectural world, the engineering world are 2 exceptionally powerful lobbies. I mean, they're massively powerful. There's an awful lot of vested interest in all of those institutions. You know, they're really seriously establishment. There are 36 different engineering institutions in this country, each one of which wants to have its own niche, plus the RIBA, who wants its own niche. And yet they're all trying to work together on projects very often. And it's hard to have a niche at the same time as you're really engaged in a shared endeavor. There have been examples of integrated practice, like Terminal 5, for example, which I think was a very good experiment in many ways, where the contractors come in as well, because I think, on Stockton, some of the most important people there were not probably the people who did the complicated calculations, or the people who worked out how the landscape was going to work at both ends, or even the people who worked out the form of the bridge. They were probably the people who worked out how to build the thing for the money that they had, and actually got out there in the pouring rain and built it. I mean, and to have that level of insight at the time you're designing things is what they tried to do on Terminal 5, not really doing on the Olympics at the moment. The contractors are all appointed after the designers. And I think, so integrating design and construction, personally I would put ahead of, I think it's important to integrate architects and engineers, but I think design and construction is more important, really. Which is why I went to Imperial basically to teach design. But after a while, it became obvious that it was pointless teaching design if people didn't have the faintest idea what it was going to turn into when it was built. People would draw the most ridiculous things that had not a snowball's chance in hell of standing up, because they had no understanding of the physical world whatsoever. So we did the construction area as a response to that, to put that into their heads. Every time they're trying to design something, you've got a physical piece of physical experience to fall back on. was another question that the next to you. Sorry, yes.
I was going to ask a very similar question actually, which was just whether you saw the professions becoming more merged or more distinctly specialised in the future.
No, I mean, what I hope happens is there are actually two strands. You need the world's best, I don't know, dynamic analyst, or the world's best facade, somebody who understands glass, or somebody who understands carpets, or God knows what. I mean, you need the world's best of those. The question is, how many people like that do you need? And increasingly what's happening is that many of the things that were done, if you need lots of beams, you had to have lots of beam analysts and lots of beam engineers, because you couldn't spread that around the world without having lots and lots of them. Now you can you can download a program which will stick the reinforcement in that and draw it for you, and actually squirt it down the wire to somebody who will build it for you. And anybody on the planet can buy that. An architect can buy that. There's no reason why an architect shouldn't design these beams. Absolutely no reason whatsoever. Fred, who did the genetic algorithm stuff, as I say, came from the water engineering fraternity and makes sculptures in his spare time. Never been anywhere near a building. Never met an architect. And yet he's done something which actually is pushing the sort of integrated thinking further than people who've been working in architecture and engineering their entire lives. So I think there are lots of opportunities for people who, just are prepared to look outside their traditional boundaries to sort of come up with something new. And as I say, the fact the world's changed is very important. You mentioned that piece I wrote with, in response to the Guardian article. And I genuinely think that we really do not need more engineers. We don't need more people who know how to put reinforcement in beams. Absolutely, and yet that's what you're taught at university. What we need is people who can join together really complicated issues, work out some way of dealing with them. And I don't mind whether they're architects, engineers, what they call themselves. They're all part of this big spectrum. And some of them will have to be specialists. Some of them will have to be generalists who can look very broadly. And the generalists need to be able to talk to the world's best facade person somehow, either personally or through a download. But given that a lot of that sort of production stuff is going to India, China, Brazil, all those sorts of places, it's likely it'd be harder to talk to them than it was in the past.
About it, but the wobbly bridge, the problem hadn't been known about before. But for many years, probably centuries, armies have known to break step when walking across bridges. So is it a different problem? How does that differ? This wasn't the problem that people were walking.
It wasn't. Yes. I mean, the basic problem
is that it's a lateral movement rather than a vertical movement. So everybody knew that if the Roman army breaking step when it goes across a bridge, you put your foot down like that, and if you're unlucky, the bridge responds, and everybody knew about it going that way. What happened on the Millennium Bridge, and we tested that, of course. I mean, we tested lots of. We also tested. It's 4 meters wide. We tested rugby teams running from one side and pushing against the side, coming back, pushing against the side, and to see if they could get it going in sequence with the speed they could run, and all sorts of things like. We tested loads of scenarios like that. And we also tested thousands of people going across the bridge, but all the considered advice at that time was that it would be people would walk at random speeds. And so, you'd be walking like this, somebody else would be walking slightly differently, and the bridge would not resonate. It turns out that, and up and down it doesn't really, but sideways, what happens is if you sense the bridge moving, you put your foot down. It's like being on a ship. You put your foot down slightly, and at the moment of putting your foot down, you give it a kick, which makes it worse. So the first person to do that gives the bridge a slight kick. And if you don't get too many people doing it, everybody else who's walking at random damp it all back down again. But if lots of people sense it, then you get past this point of no return, at which point they're all kicking in time, kicking that way, kicking in that way, and they're all moving. The bridge moves, they're all moving in time, just like being on a boat, at which point it has to reach a new equilibrium, which is moving sideways. That phenomenon of people locking in, sensing the movement of the bridge and locking in, it's fundamentally driven by long-span, very light bridges, which haven't existed until the last few years. So, you can look at, and I know there are bridges around the place that wobble all over the place. I know there are swing bridges in Nepal which do the same thing. actually. And in fact, in Nepal, if you look at the cable bridges, the suspension bridges, they often put a sideways cable on them to stop them doing exactly that. Now, all of those sort of simple things we tested, but we'd never thought that 1,000 people would lock themselves in. So on Stockton, it's got 7 dampers slung underneath, integrated into those little cavities on the underside of the deck have TMDs, which hopefully, well, the acid test comes in about a month, will stop it wobbling. But that phenomenon wasn't seen. And if people ever saw it, I mean, people tend not to publicize their failures if they can possibly avoid it. So it may well have happened before. I mean, in fact, there was one in Canada and there was one in Japan, but they weren't widely publicized. You know, you live and learn. Anyway, I think that personally, I'm delighted to have been involved in the Millennium. I think it's a fantastic project, and I think that warts and all, it's great. I really like Stockton too, but as I say, I think it's there are some quite big questions out there which you can't answer with a beautiful bridge. Any more questions? Okay. Okay. Are you going to ask one?
You ended on it.
Oh, did I? Right. Well,